All right, so you guys just saw this demo, and it's a pretty cool demo. Basically, what it means is that you can control the motion of wire with electricity, and yes, and magnets, right? But in this case, instead of having one charged particle like we did yesterday, we have like lots and lots and lots of charged particles moving, and so you can get something to go a whole wire to move. All right. So the derivation. One of the neat things about this is the basic idea of is QV cross B, right? QV cross B is the force on a charged particle. How do you get the force on a wire? Well, you just say you have a little piece of wire that has a charge that's moving, right? And so you instead of writing dQV, we know I is dQ over dt. So dq is I dt. But
velocity equals dl dt.
Right, velocity is dl dt. Wow, that was really sloppy. Right, velocity is dl dt. So dt is dl over v, blah, 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 blah. In the end, dq times v is the same as I dl. And so that's where this equation, I dl cross b, comes from. That's on your equation sheet. All right, moving on. That was not very helpful. Okay, what this means is if you have a wire, you don't have to do all sorts of crazy angles or anything like that. You can just say ILB sine theta is the force, or BIL sine theta. Remember the Bill equation?
Yes.
Yeah, this is it.
Oh.
Comes from Biot-Savart law. It's just without any integrating. All right. Now, let's imagine, say, we had two wires running parallel to each other. You have wire 1 and you have wire 2. All right, here's wire 1, here's wire 2. What direction are the currents going? Same direction. So let me ask you this. Pretend like wire 1 wasn't there. Would there be a magnetic field at the location of wire 1? Why? From wire 2. Wire 2 is creating a magnetic field right there. Agree? So wouldn't you agree, therefore, that wire 1 is sitting in the magnetic field of wire 2? Okay, so doesn't that mean that wire 1 is going to be pushed by that magnetic field? Which way will wire 1 be pushed by that magnetic field from wire 2? So, in other words, you got to figure out which direction the field is. Everybody pull out your right hand. Which way is the field where wire 1 is sitting? Not up. Out of the page, right? So the field's out of the page right there. So which way does wire 1 get pushed? See, the field is out of the page. The current is to the right. So wire 1 gets pushed down. Got it? So wire 1 gets pushed down. What way does is wire 2 sitting in a magnetic field?
Yes.
From which wire?
Wire 1.
From wire 1. Which way does wire 2 get pushed?
Oh. Towards.
See, the field is into the page, right? The current is moving to the right, therefore wire 2 gets pushed up. So which way did wire 1 get pushed? Down. Which way did wire 2 get pushed?
So it's attractive.
It's an attractive force between the two of them. That's that interesting. So that means if you have two parallel wires with the same current running in them, guess what's going to happen? They're going to attract each other. Sound good? All right. And moreover, if you do a little math, you could figure out how strong that force is. And what you could do is you could figure it out and, I don't know, go through this whole process. The field at 2 is mu naught I over 2 pi d from before, right? So the force on 2 is the field at 2 times the current of 2 times the length of 2, which means the force on 2 is mu naught over 2 pi I1 I2 L over d. Good? So, more force if they're closer together. More force if there's more current through one. More force if there's current through two. And the total force depends on how long the wires are too. Does that make sense? So, this actually has some interesting effects. Have you ever seen two wires running parallel to each other before? Power lines, yeah. What about two wires running even closer to each other than power lines?
In one of those cords.
Yeah, one of these cables. Let's see if I can find one here. Oh, here we go. Here's one with two wires running parallel to each other. You ever notice that? It's got plastic on the outside, but you've seen cables like that,
Yeah.
right? Let's say those two wires, in this particular case, one current is going one way and the other one is going back the other way. Agree?
Okay.
So is that going to repel or attract? So these two wires are repelling each other, which is fine. But what if you had cables where you had two wires running the same direction? Say you had one powering your, your computer, and another one powering your television or something like that, running parallel to each other with the same current going in each wire. What would happen to those two wires? They would be attracted to each other. Okay, fine. So they're attracted to each other, which if it were direct current would be no big deal. But what if they're two power cables? What are power cables? Alternating current. So what's going to happen to the force?
They'd eventually shake themselves apart.
You've got wire 1 attracting wire 2 and wire 2 attracting wire 1. But what happens in the point in the cycle when there's no current?
When there's no current?
When there's no current, are they going to attract?
No. So they just
So
swing back to their normal.
every 120th of a second, according to the sine wave, it's 60 cycles a second, so every 1/20th of a second, there's no current, so there's no attraction. And then there's lots of current, so there's lots of attraction. Then no current, then no attraction. What are these two wires going to do? You see the problem with this over time?
Yeah.
What's eventually going to happen? The plastic on the outside eventually is going to come apart. And you're going to have a situation where you have two power cables next to each other, and the plastic just demolished itself. And what ends up happening?
You shorted.
Short circuit and a fire.
So then, what do they do to prevent this?
What do they do to prevent this? It's a great question.
Do they like magnetically
Like,
shield
this
it?
happens all the time in your house. Two wires running parallel to each other.
Yeah. No, I don't know.
So how do you prevent that from happening according to this equation? Or you can't totally prevent it, but how do you minimize it?
Decrease the amount of current.
Okay, let's say you can't decrease the amount of current because the device takes a certain amount of current.
Increase the distance.
You either, if you have to run wires parallel, you keep them far apart so that they can't smack into each other.
Or you put them really.
Or-
is running in the opposite direction.
Or make sure they're never running parallel.
Oh.
And one of the installations I worked at in the Navy, this is actually a big deal. We had to take all our wires and make sure whenever a cable was going to one piece of equipment or another piece of equipment, they never went like this. We always made sure they crossed perpendicular. Because if they cross perpendicular, is there going to be any force?
No.
No.
What's it say?
All right. So let's move on. So we did. Let's see. We did force on a wire. We did making a speaker. See, what haven't we done? Have you guys? Have you seen a railgun before?
Could you
No.
theoretically make something that launched someone in space magnetically?
Absolutely. You can make a launcher that launched things into space. Yeah. Hey, do you guys know what a railgun is?
Yeah.
Yeah.
Have you ever seen one before? Really?
Transform.
We actually have one here in real life. Do you guys want to see it?
Yes.
All right. So.
Okay, hold on. Let's be not accepted.
Why do you not trust physics?
I trust physics.
All right, so hold on. I gotta get this set up.